Section 2.4 Congruent Supplements and Complements by Kieran Beckham. The objective of this section is to be able to prove angles congruent by the means of 4 new theorems. In the diagram below, angle 1 is supplementary to angle A, and angle 2 is also supplementary to angle A, as you can see. How large is angle 1? So to calculate angle 1, we have to take 180, because that's the degree of a straight line, which forms a supplementary angle, and subtract 70 from it. So we would get 110. Therefore, angle 1 is equal to 110. But because angle 2 is also supplementary to angle A, it's the same degree as angle 1, so it is also 110 degrees. Angle 1 is congruent to angle 2 because they both equal 110 degrees and are both supplementary to angle A. Here's our theorem number 4. If angles are supplementary to the same angle, then they are congruent. This is why angle 1 and angle 2 are congruent. Here's our given statement. Angle 3 is supplementary to angle 4, and angle 5 is supplementary to angle 4. We have to prove that angle 3 is congruent to angle 5. Our proof will look something like this. Angle 3 is supplementary to angle 4, so the measure of angle 3 plus the measure of angle 4 is equal to 180 degrees. Therefore, the measure of angle 3 is 180 minus measure of angle 4. Angle 5 is supplementary to angle 4 as well, so the measure of angle 5 plus the measure of angle 4 will be equal to 180. Therefore, the measure of angle 5 is equal to the measure of 180 minus the measure of angle 4. Since angle 3 and angle 5 are both equal to 180 minus the measure of angle 4, they have the same measure. Therefore, angle 3 is congruent to angle 5. So this is the proof for theorem 4. Here's theorem 5. If angles are supplementary to congruent angles, then they are congruent. So our given statement is that angle F is supplementary to angle G, angle H is supplementary to angle J, and angle G is congruent to angle J. We have to conclude that angle F is congruent to angle H. And the proof of theorem 5 is similar to that of theorem 4 because they both apply to complementary angles. Sorry. Here's theorem 6. If angles are complementary to the same angle, then they are congruent. And theorem 7. If angles are complementary to congruent angles, then they are congruent. When studying the definitions of such terms as right angle, bisect, midpoint, and perpendicular, you will master the concepts more quickly if you try to understand the ideas involved without memorizing the definitions word for word. The theorems in this section, however, are different. Unless you memorize theorems 4 through 7, you will have difficulty remembering the concepts they contain. Therefore, here's your homework. You must memorize theorems 4 through 7 and read the sample problems carefully so that you understand which of the theorems is used in each type of problem. So we have a sample question here. Problem number 1. Our given is that angle 1 is supplementary to angle 2 and that angle 3 is supplementary to angle 4. And we have to conclude that angle 2 is supplementary to angle 3. So our first 3 givens are here. Angle 1 is supplementary to angle 2, angle 3 is supplementary to angle 4, and angle 1 is congruent to angle 4. Because the angles are supplementary to congruent angles, they are congruent. This is the theorem that we learned. Theorem number 5. Where is it? Right here. Theorem number 5. If angles are supplementary to congruent angles, then they're congruent. So our conclusion is that angle 2 is congruent to angle 3 because of theorem 5. Thank you.
Section 2.5 Addition and Subtraction Properties. The objectives of this section is to apply the addition properties and subtraction properties of segments and angles. In the diagram below, AB, which is this, is equal to CD. Some questions we need to ask are, is AC equal to BD? And if we were supposed that BC is 3 centimeters, would AC be equal to BD? If AB is equal to CD, does the length of BC have any effect on whether AC is equal to BD? Our answers to these questions should be that AC is equal to BD in each case, and the length of BC does not affect that equality. This is a geometric application of the algebraic addition property of equality. So here, for this, it would be AB plus BC is equal to CD plus BC. Theorem 8 is, if a segment is added to two congruent segments, the sums are congruent. We are given that segment PQ is congruent to segment RS. Our conclusion is PR is congruent to QS. Our proof is, by definition of congruent segments, PQ is equal to RS. The addition property of equality says that we may add QR to both sides. So PQ plus QR is equal to RS plus QR. When we substitute, we get segment PR is congruent to segment QS by the definition of congruent segments. Does the similar relationship hold? Is the relationship similar for angles? If angle EFH is necessarily congruent to JFG, the next theorem confirms that the answer is yes. Its proof is like that of theorem 8. If an angle is added to congruent angles, the sums are congruent. In the figures below, identical tick marks indicate congruent parts. A question we can ask is, do you think segment KM is necessarily congruent to segment PO? In the right-hand diagram, is angle TWX congruent to TXW? The answers to these questions are yes. These congruencies are established by the following two theorems. Their proofs are similar to that of theorem 8. The two following theorems are theorem 10. If congruent segments are added to congruent segments, the sums are congruent. Theorem 11 is, if congruent angles are added to congruent angles, the sums are congruent. Subtraction properties. We now have 4 addition properties because subtraction is equivalent to addition of an opposite. We can expect 4 corresponding subtraction properties. Some questions we can ask are, if AC is equal to BD, is AB equal to CD? Let AC be 12 and BC be 3. How long is BD? Is AB equal to CD? If a segment or angle is subtracted from congruent segments or angles, the differences are congruent. If congruent segments or angles are subtracted from congruent segments or angles, the differences are congruent. Problem 2 is, we are given segment GJ is congruent to segment HK. Our conclusion is GH is congruent to JK. Our proof would be, we are given JG is congruent to HK, and we can assume that GH is congruent to JK, because if a segment, which is HJ, is subtracted from both congruent segments, the differences are congruent, which is from the subtraction property.